Morning guys, so let's actually start, yeah. So Nicole, can you hear me? Clear, yeah? Alright. So now, okay, I will start. Okay, so you see here, okay, group 2 elements are metals that react with oxygen and water. Okay, write the electronic configuration of magnesium atom, yeah. So if you want to write the magnesium atom, okay, quite simple, yeah. So you should know, you refer to your periodic table. Okay, magnesium is 12. So 1s2, 2s2, okay, 2p6, okay, that's already 10, okay, and then 3s2, okay, so 4, 10, 12, yeah. So you write down, okay, 2p6, sorry, 2s2, 2p6, and 3s2. Okay, quite simple. Now next, okay, the trend in the first and second ionization energy of group 2 elements, okay, can be linked to the increase in the chemical reactivity down the group. Okay, so the first and second ionization energy of group 2 elements can be are given in the table. Okay, write an equation including state symbols to represent the second ionization energy for strontium. Yeah, second, yeah, please remember. Okay, when they say second, it means they have already lose one electron. Yeah, strontium. So strontium, they already lose one electron. They are going to lose another one more electron to give you strontium 2 plus. Okay, so it means plus electron, they lose the electron. Okay, include state symbols. In order to get this 1 mark, state symbols must be given. Okay, it must be in gaseous form. Okay, remember that. Okay, so that is done. Explain why the second ionization energy of strontium is less than the second ionization energy for calcium. Okay, so why? Okay, so in order to know that, okay, you need to write down, okay, the electronic configuration, yeah, for calcium and strontium. Okay, so let's actually look at the periodic table. So we are looking for calcium and strontium. Okay, so better if we want to find out for this, okay, we use the shorthand method, yeah. So argon, okay, for calcium, I'm going to use argon. And then this is argon, so this is 2, 3, 4. So 4s2. Okay, 4s2. And then for strontium, that is going to be, okay, we look at krypton. Krypton. Then after that, okay, 4s2 also. Okay, so I'll just bring this. And I put it here. Now, in this case, okay, when we want to explain, okay, the ionization energy of strontium is less, okay, so do remember, okay, there is nothing to do with when they are, sorry, I think this one is 5s2, my mistake. Okay, 5s2. Okay, so what we need to remember over here is, okay, to remove the first electron, yeah, you remove from 4s, you remove from 5s. But, okay, when you want to have the second ionization energy, you are removing the electrons, okay, each from 4s and 5s. But they are telling that you want to remove the from 5s is actually less than the second ionization energy of calcium. Why is that? Okay, so the reason, okay, let's see, Calista, can you try to figure out why it might be less?
Because it comes from different
what?
From
It's almost there, Calista. It comes from different what and why? What is the difference? Yeah. So basically, you need to mention, it is coming from the different principal quantum shell, if you want to use the term shell, So it comes from different principal quantum shell, or you can say it comes from, 5s orbital, which is further away, from the nucleus, making the attraction from the nucleus, towards the electron, is shielded by many electron shells. So the attraction of the nucleus towards the electron is weaker compared to calcium. So that is the idea of it. That is the idea of it. But let's actually look at what the marking key says. So what they want you to answer, you can just have a look over there. They want you to answer, atomic radius. So you talk about, strontium has a larger atomic radius, or you mention more shells. Just now I mentioned about more shells. So any of these, and you mention about, increased nuclear charge outweighed by the increase of the distance of shielding, or you say more or increased shielding, and then nuclear attraction, less nuclear attraction. So you see, there are 3 points that they want you to answer. So it means now you are going to explain based on strontium. So please remember this one thing. One thing that I noticed with our students, is when they ask about strontium, you go and explain about calcium. They are asking you to compare, yes. But the question is about why about strontium. So you don't go and explain about calcium. I give you a simple example. Let's say you have boy A and boy B. And then the question is, why this girl go and selected boy A? Why this girl go and select the boy A? You don't go and answer boy B is ugly. You don't go and answer boy B is ugly. Instead, your answer should be boy A is more attractive than boy B. So it means I want you to actually focus on that. Because a lot of students actually go and discuss about the other one. You need to discuss about strontium. So it means your prime focus must be about strontium. So strontium, because they are actually have more shells. So you can actually just mention, strontium has larger radius and it has more shells than calcium. More shells than calcium, and because of that, even though there is strontium has more I think nuclear charge, even though there is increase in nuclear charge, the shielding effect, outweighs it. When I mean it means it is outweighs nuclear charge. Do not simply use the term it. So the shielding effect outweighs it. Making let's continue. Also outweighs it. So shielding effect, I'm talking about shielding effect, and you can say because of that, less nuclear attraction towards the 5s orbitals compared to 4s orbitals in calcium. Okay, so I have explained that, yeah, even though I'm actually trying to put more, okay, more answer there, but I want you to realize, okay, this answer that I have mentioned over here, okay, it has something to do with atomic radius. It has, okay, it has the more shielding, yeah, outweigh the distance, okay, so it is outweighing the distance, outweighing the nuclear charge. And then, okay, it has less nuclear attraction towards the electrons. So if you look at my answer now, okay, you see it has larger, okay, larger radius, okay, and I mentioned more shells. That's going to give me 1 mark. Okay, and then even though there is nuclear charge, the shielding effect, okay, the shielding outweighs it. Okay, so I mentioned about shielding now. That's going to be another 1 mark. And then less nuclear attraction towards the 5s orbital, which I am defining related to strontium. Because how do I know it's related to strontium? Because the question is asking about strontium, and I have mentioned that I'm talking about strontium. Yeah, less attraction towards the 5s orbitals compared to 4s orbitals in calcium. Yeah, or less nuclear attraction towards the electrons. Okay, electrons in 5s orbitals of, okay, strontium, if you want to make it more clearer, okay, compared to 4s orbitals in calcium. Then, okay, if you have time, you write down. Then it is much more easier to remove the second electron from strontium compared to second electron from calcium, if you have time. Okay, but for us, okay, we already have the 3 points. Okay, no need to explain further. Okay. So please remember, yeah, what are the points that you need to mention? Okay, you need to mention about radius, shielding, okay, and related to shielding, you need to relate again. Okay, it will outweigh the increase in nuclear charge. It will outweigh the distance, increase of distance, and then you talk about nuclear attraction. Very important, yeah, these 3 points. Now, next, the first ionization energy of elements across the third period shows a general increase. I think this one we have already learned, yeah. So if you have a periodic table, generally when you go across the periodic table, the radius generally becomes smaller. Okay, they become smaller. Okay, now aluminium and sulfur, okay, aluminium and sulfur do not follow this general trend. Okay, explain, okay, why aluminium has lower first ionization energy compared to magnesium. Yeah, so they say aluminium and sulfur do not follow. Okay, and then I'm just asking to compare. Okay, so it means they are not going to talk so much about sulfur. Yeah, so why aluminium has a lower first ionization energy compared to magnesium? Yeah, so that is the question over here. So we are going to focus on aluminium or magnesium. Let's see whether you guys are following what I said. Yeah, so Vanessa, is my main answer, my main focus is related to aluminium or magnesium?
Aluminium.
Yes, yeah, your main focus of your answer must be based on aluminium. Yeah, so let's actually write down for aluminium. Aluminium is 13, so 1s2, 2s2, 2p6, that's already 10, 3s2, 3p1. Okay, magnesium, okay, is 12, so 1s2, 2s2, 2p6, and 3s2. Okay, so they are telling, okay, aluminium has lower. Yeah, why lower? Because the first ionization energy, okay, it deals with removing the electrons from 3p1. Okay, let's actually plan our answer. Yeah, the first ionization energy, okay, involve removing the electrons from 3p1 orbit, 3p subshell. Okay, you can mention subshell. Okay, so it removes, okay, the electrons from 3p subshell, and this 3p subshell is further away from the nucleus. Okay, further away from the nucleus, and it is if it is further away from the nucleus, it is easier to remove the electron. For magnesium, 3s, it is removing the electrons from 3s subshell, which is closer to the nucleus. Closer to the nucleus, which is, we have to actually mention that the nuclear attraction towards the electrons in 3s subshell is greater, making it harder to remove. So that is my plan. You see, based on that plan, does our answer key corresponds to that? It should correspond to that. You see here. So you see here, the outer electron, the electron is removed from the 3p subshell. So just now I used subshell. So do remember, this is for what? Aluminium. So you see, aluminium, I'm talking based on aluminium. And you talk about 3p. The 3p is higher in energy, more shielded or further from the nucleus. So I'm using the term further from the nucleus. So they are not giving mark for magnesium, even though I say it is, I'm still explaining, it is closer to the nucleus, and so on. They are not giving any mark for me, but maybe if I want to explain, I can still explain. But you see, so when I want to write my answer for this, you just need to answer that aluminium. Always start, when they're talking about strontium, you start with strontium. So you say, you just start aluminium. Or you can say for aluminium, the electron is removed from 3p1 subshell, which is further away from nucleus. This makes the nuclear attraction weaker and less energy is required to remove it. So I'm still not actually mentioning about magnesium, but if you have time, please mention. Then if I have time, I would have continued. For magnesium, I'll continue. For magnesium, the electrons are removed from 3s, which is closer to the nucleus, which is going to be, the nuclear attraction is more stronger and more energy is required to remove it. So that's going to be more. But according to what I mentioned to you last time, Cambridge do not want students to keep on writing long answers, because they find that students tends to contradict their information, contradict their points, and you will end up losing a lot of marks if you contradicting to your points. So please take note of that. Be very precise with your answers. Now, so far, 7 marks. Everything okay? Nicole, okay? Felicia, okay? Jessica, okay? Alright, 7 marks. Let's actually move on. Combustion data can be used to calculate the empirical formula, molecular formula, and the relative molecular mass of many organic compounds. Define the term relative molecular mass. So if you define, first you need to mention about relative to what? Molecular mass, is for molecule, molecular mass. So you need to actually mention, relative molecular mass is going to be the mass of a molecule, a mass of molecule, in comparison or in relative to okay, in relative, rather than using the word relative again. Okay, mass of a molecule in comparison to 1/12, okay, 1/12 of the mass of one atom of carbon 12, okay, the isotope, yeah, so we need to follow the 1/12 of the mass of one atom of carbon 12, okay. I think that's all, yeah. Okay, this is based on what I know, that should be the answer, yeah. So let's see what is actually the marking key. Okay, the mass of a molecule, okay, in relative, okay, or compared to 1/12 of the mass of an atom of carbon 12, yeah. So I think we get the answer already, yeah. So we will follow this one. Okay, done. Now the next, okay, is going to be T is an alcohol, yeah. So they give you this, a gaseous sample, they occupy this volume, this temperature, this pressure. Now whenever you have all these values, yeah, do remember maybe only, yeah, maybe is related to PV equals to nRT, maybe only, yeah. But we continue. The sample was completely burned, okay, using oxygen. The final volume, okay, measured under the same conditions as the gaseous sample, okay, was 250, okay, the final volume. Okay, under this condition, all the water present is vaporized, so all the water is actually gases. Removal of the water, okay, from the gaseous mixture decrease the volume, okay, to 170. So it means that water, yeah, so I know the volume of water from here, from this information. They say after you get everything, final volume was 250. Then you remove water vapor, it became 170. So I know the volume of water vapor is 80. Okay, this is the first information that I get. Okay, treating the remaining gaseous mixture with concentrated alkali, okay, to absorb carbon dioxide, okay, decreases the volume from here to here. Okay, so what actually absorb, okay, carbon dioxide? Okay, it means concentrated alkali absorb carbon dioxide. Okay, it means this is the volume of carbon dioxide. Okay, so volume of carbon dioxide, you can just write down volume of carbon dioxide from 170 to become 110, so must be 60. These are the information that I'm getting, yeah. So it means once I get this, you no need to worry about this point. Okay, you no need to worry from I think from this point to this point, you no need to worry. I'm summarizing over there. The equation for the complete combustion can be represented as shown, yeah. So they give you all this, and then they say that just now you completely burn with 200 cm³ of oxygen, which is excess, yeah. Not everything is actually being used. Okay, so if you have, okay, this one water, water is going to be 80. Okay, this is going to be 60, confirm. So if confirm, I just circle. 200 is not confirmed. Okay, 200 is not confirmed. The gaseous sample of T occupied the volume of 20. Okay, so it means this one is going to be 20 here. 20 at 120 degrees. The sample completely burned. The final volume measured, okay, of the gas sample, okay, which is the final volume was 250. Final volume, okay, measured under the same condition, 250. Okay, hold on, yeah, I'm still figuring out the 250 means they are talking about this one, okay, then 250, the final volume. To absorb, decrease the volume to 110. Okay, because this one decrease the volume to 110. So these two supposed to be 110. So if this one is extra, yeah, don't know whether I'm correct or not. Yeah, if this one is, if I want it together to be 110, then this one should be 90. Yeah. So you have 20. Okay, 20. Then you have a lot of oxygen, which is 200. Okay, and then the final volume measured was 250. Okay, because I used this 20 over here. So if I have 110, okay, then 170 and 80, so 250. Yeah, according to what I have, yeah, that is supposed to be the one that's supposed to be reacting. Yeah. So with this information, let me actually try to do this. Yeah. So do remember, all these are gases. You do not need to change them into number of moles. Yeah. So you can just straight away use, okay, directly. So here, okay, what I can notice over here is use the data given to calculate the value of X. Okay, you see here, 1 mole, okay, 1 mole, okay, to change into this, you see here, from 20 to become 60. Yeah, Felicia Rufus, what might be the value of X? This X, from 20 to become 60. How 60 formed from 20? Times by what? Louder, or you type, Felicia? Times by 3, yeah? Okay, times by 3. So you see, X must be 3. Okay, X must be 3. So use the data, calculate the value of X. Okay, if you want to show the working, 60 divided by 20 is 3. Okay, X I calculated is 3. Okay, then, okay, I know X is 3 now. So let's actually calculate for Y. Okay, so Y, okay, how do I calculate for Y? Okay, if I have, okay, C3, okay, C3HYO plus ZO2 to give you 3CO2 plus Y over 2 H2O. Okay, now how to calculate from here? Okay, 20 to become 80. Okay, nickel, if this is 1, 20 to become 80. Okay, this entire thing should be what number, nickel? What is 20 to become 80? Times by what, Nicole? 4. It means this value, the entire value must be 4. Okay, the entire value must be 4. So it means that Y over 2 equals to 4. Okay, Y over 2 equals to 4. So what is Y? Y is going to be 2 times 4, which is 8. That's 8. Okay, so if I rewrite this, okay, it's going to be 4. And then now, if this is 4, can we write the balance equation? Okay, so it means this is the working for this, yeah? Okay, so you want to write the balance equation. How many oxygen do we have on the right, yeah? Because we want to balance over here. How many on the right? So maybe Audrey, can you tell me how many oxygen on the right? 3 times 2, 6. Audrey?
10.
10. So I need 10. You have 1 over here. Okay, so what is the value of Z over here, Audrey? You have 1, so you need 9 O, right? But you have O2. Yeah, so 9 over 2. Yeah, good. So you need to actually put 9 over 2 over here. Okay, 9 over 2. Okay, in chemistry, okay, we try, okay, to bring, yeah, because they want complete combustion, we try to bring the 2 over there. So everything times by 2 is 2C3H4O. They mention it's gas, yeah, everything. So plus 9O2 gas to give you 6CO2 gas, everything times by 2, yeah, 8H2O gas. Done. Okay. So if let's say you didn't manage to calculate, if you will only lose 2 marks, you can also use the value that is given. Okay, the value might not be correct. You see, the value they give you 4, they give you 10. Yeah, it's not actually correct. Okay, but you still can use that to get this answer. Yeah, you won't lose mark. Yeah. So anyway, use the general gas equation, okay, to calculate the mass of T. Okay, so now I know it's C3H4O. Okay, T. Present, okay, I want to find the mass present in the original 20 cm cube. 20 cm cube gas sample, which was measured at 120 degrees Celsius, 100 kilopascal. Okay, when they say general gas equation, yeah, what is the general gas equation that they mean? Yeah. So this one, sorry, this one I told you in the beginning itself. Okay, they are talking about PV equals to nRT. Okay, pressure you must use Pascal. Yeah, so change 100 times 10 to the power 3. Okay, kilo means 10 to the power 3. Volume must be in meter cube. Yeah, so 20 cm cube is 20 times centimeter, because some of you still do not know this. Yeah, and then centi is 10 negative 2 meter, 10 negative 2 meter, 10 negative 2 meter. So that will become 20 times 10 negative 6 meter cube. Okay, so this one I'll just put 20 times 10 negative 6. Number of moles, okay, in this case, the mass, yeah, the mass, I want to find the mass, divide by mR. Okay, mR for this, 3 times 12 plus 4 plus 16, yeah. So you will get 36 plus 4, 40, 40 plus 16, 56. So 56, R is 8.31. You can get it from the question itself. Yeah, 8.31 gas constant. Yeah, temperature must be in Kelvin. Yeah, please remember 120 plus 273. Okay, all this information will be given. Yeah, you can see here. Okay, 8.31 is given. Okay, and then you need to add 273. Okay, so you get 393. So the mass, okay, you help me to calculate there. 56 times, this is 10 to the power of 5 times 10 to the power of negative 6 times 20 divided by 8.31 times 393. Help me to calculate. 0.343 times 10 negative 1. So I can just write down as 3.43 times 10 negative 2. Okay, let's see the answer. PV equals nRT 120, okay, divided by 831,393, okay. Calculate and answer to this. 60. I got 56. Okay, hold on, yeah. Just now did I make mistake? This one 36 plus 4. Oxygen how many? Oxygen is 1. (36) plus 4 plus 16, so that's going to be 20. 56, yeah. I think marking key is wrong, yeah. C3H8O. Oh, my mistake, yeah. C3H8. Y is 8. I go and put 4, yeah. Okay, wait, yeah. I think Y is definitely 8. Okay, why I put 4 there? Oh, because I thought it's... Okay, hold on, yeah. Y is 8. Okay, Y is 8. So if Y is 8, okay, 8 is all correct. This one 9/2, everything is correct. So only this one is 8. All balance. So this one will become 8, 60, yeah, 60. So this part is divided by 60, and then this part is 60. The answer should be 0.0367. 0.0367. (0.0367). Yeah, just take note of that. Yeah, so I made a mistake over here. So this one is C3H8O, so supposed to be 60. Okay, so that's what you are going to get. Okay, now that's already another 6 marks. Okay, so let's actually move on. This is going to be interesting question. Yeah, recently only we learned. Okay, so you have 3 hydrogen atoms of methane replaced by halogen atom. Okay, the equation shows a reaction to produce CHF3. Yeah, so to produce this, okay, use the data to calculate the enthalpy change of the reaction for this formation of CHF3, and all the information about formation is given. Yeah, so Audrey, okay, if I have formation, what method do I use, Audrey? There are three methods of calculating: rearranging, triangle, Mr. Gopi's method. So which one? You don't know. You haven't go through the video also. Okay, make sure you learn this. Yeah. So formation. Yeah. So Mr. Gopi's method. Yeah. CHI3. So follow the arrow to form. Okay. CHF3 to form. Okay. AGF to form, but 3 times. AGI to form, but 3 times. 3 times what? Negative 61.8. CHF3 is negative 692.9. AGF is going to be negative 204.6. Okay, this is negative 182.1. Okay, then you put a circle there. Clockwise equals to anti-clockwise. Clockwise, negative 182.1 plus. Okay, this one all will go clockwise. This one will look like anti-clockwise. Clockwise also. Okay, so plus 3 times negative 204.6 plus, okay, enthalpy change of reaction equals to negative 692.9 plus 3 times negative 61.8. Okay, enthalpy of reaction is plus 182.1 plus 3 times 204.6. So you just need to calculate that. Negative 692.9 minus 3 times 61.8 plus 182.1 plus 3 times 204.6. Negative 82.4. Okay. Okay, so next question, the graph shows the relationship between PV and P, yeah, at a given temperature. So this is ideal gas, this is deviating from the ideal gas. So they say it's not an ideal gas. State 3 basic assumption. Yeah, when they say basic assumption, follow the important points first. Yeah, there should be no intermolecular forces between the gaseous molecule. Then the volume of the gas particle, yeah, so be specific. The volume of gas particle is negligible because the distance between the molecules is too big. Okay, and then the last number 3. Okay, one more. Kalista, one more. The collisions are all elastic. Yeah, please remember all this. Yeah, the collisions are all elastic. Okay, so of course there are others. Yeah, like for example temperature increase, okay, the entire average kinetic energy will increase and all that, okay, and then they always move in rapid and random manner. Yeah, those are applicable for all gases. Yeah, so the one that is important, yeah, is these three. Yeah, these three. Don't simply give everything. Now explain, okay, but you see I started off with these two, yeah, because these two are the most important. Yeah. Explain why CHF3 deviates from the property, okay, at pressure greater than 300 atmospheric pressure. So why they deviated all the way at higher pressure, okay. So basically, okay, at higher pressure, okay, what happens, okay, when generally, okay, if you have higher pressure, they are going to go closer to each other. Okay, when they are closer to each other, you cannot ignore the intermolecular forces of attraction. Yeah, so let's actually look at what kind of intermolecular forces of attraction that can happen. Okay, in this case, this is F and F. So just want to know, okay, whether this one is polar or non-polar. So Vanessa, is this polar or non-polar, Vanessa? Polar. Okay, if you have F over here, then the dipole moment will be cancelled out. In this case, it's not cancelled out. Yeah, so you can just write down CHF3 is a polar molecule, and at pressure more than 300 atmospheric pressure, the intermolecular forces which is, okay, for polar you must mention permanent dipole, PD, yeah, permanent dipole or permanent dipole forces becomes more prominent and cannot be ignored. Okay, so that's the answer. Okay, let's see the answer key. B2, yeah. B2 particles are close, okay, and then molecular size becomes significant, or intermolecular forces becomes more significant. So they are talking about intermolecular forces becoming more significant and particles getting more closer. Yeah, so even with this answer, I'm not going to get 2 marks also. Yeah, I will actually get only 1 mark. Yeah, so I think they still won because greater pressure. Okay, so which is permanent, rather than saying more prominent. Okay, more prominent because the particles gets closer. Okay, so that will be the answer for this. Yeah, total 8 marks. Okay, so here, okay, let's start. So this question is about compounds that contain fluorine. Yeah, so explain in terms of structure and bonding, okay, why the melting point of sodium fluoride is high. Yeah, so why sodium fluoride is high? So you need to know that, okay, when we are talking about sodium fluoride, okay, in terms of structure and bonding. Yeah, so the bonding, what type of bonding? This is sodium fluoride. Sodium is metal, F is non-metal, so this is going to be ionic bonding. So your answer must have, okay, combination of this ionic bonding and then the structure. Now do remember, anything that is going to be related to ionic bonding, okay, must have a giant ionic lattice. Yeah, these two important stuff must be there. Yeah. So we need to actually mention that sodium fluoride, okay, contains ionic bonding. Yeah. And then, okay, they have a giant ionic lattice where, okay, the sodium ions and the fluoride ions, okay, will have, okay, multiple or many, okay, ionic bonds, okay, that will hold each other so tight, okay, until, okay, it requires a very high energy to break them. Yeah, so that is going to be our answer. Yeah, but if you look at the marking key, okay, I'll show you what are the things expected from you from the marking key. So here, okay, they are asking for you to say that, okay, there is going to be electrostatic forces of attraction, okay, between the oppositely charged ion, okay, which is going to be Na plus and F minus. And as I mentioned to you just now, lots of energy needs to overcome and break them. Okay, so we are talking about, okay, strong ionic bonding, strong forces, strong attraction, but they didn't mention about giant ionic lattice. Yeah, so probably in this case, okay, maybe, okay, should be more answer should be accepted. Yeah, but again, okay, let's actually follow the marking key. So it means now, okay, according to the marking key, and then I will also include whatever that I feel is correct also. Yeah, so here, okay, sodium fluoride, okay, NaF, okay, contains it is going to be ionic bonding. Yeah, so it's going to be NaF is an ionic compound, okay, that has strong electrostatic forces of attraction, holding, okay, attraction holding oppositely charged ions, in a giant ionic lattice structure. So therefore it requires a lot of energy to overcome the forces of attraction. Okay, in this case, okay, I just want to summarize over here what is important over here. Okay, it is an ionic compound. Okay, it has strong electrostatic forces of attraction. Okay, and then I'm also feel that giant ionic lattice structure is important to be mentioned. Yeah, but the answer is they focus more on strong electrostatic forces of attraction, and it requires more energy to break them. Yeah, so this is a complete answer. Yeah, if you want to answer this. Yeah, now if you look at this B, okay, the ion, okay, H2F is formed, okay, when okay, we'll revisit the marking key later. Now the ion H2F plus is formed when hydrogen fluoride, okay, gains a proton, okay, as shown in the equation given. Yeah, so name the type of bond formed, okay, when HF reacts with H plus, and explain how this bond is formed. Now do remember HF. Yeah, so when they if I draw the cross dot diagram, okay, it will look like this. Okay, because fluorine contains 7 valence electron. Okay, and you can see there are total of 3 lone pair of electrons. Okay, 1 bonding pair, 3 lone pair of electrons. And when you have H plus means they don't have any electrons. Yeah, no electrons. So what will happen? This electron will be donated directly or shared directly. Okay, so this type of bonding is going to be called, what is this type of bonding, Olivia? Sharing of electrons, where you share the pair of electron. Hurry up, guys. Jolene, okay. Eshana wants to answer. Okay, Jolene, yeah.
Coordinate or the
Okay, so coordinate bonding. Okay, so don't say hydrogen bonding or covalent bonding, yeah, Ishana, so it's wrong, yeah. So type of bonding, it must be coordinate bonding, or you can answer dative bonding. Okay, so you need to mention this specifically. Okay, explanation. Okay, F. Okay, the fluorine atom. Okay, in HF contains, okay, lone pair of electron which can be shared directly to H plus ion. Okay, this is my answer. Okay, let's check with the answer scheme given. Type of bonding, okay, coordinate bond or dative covalent bond. Yeah, so there must be dative here, even though you mention it's covalent. Yeah, it must be dative, must be given. Okay, just because the word covalent is there, I need to give answer mark. No, it doesn't work that way. Yeah, so it must be dative or dative covalent bond. Yeah, explanation: a lone pair of electron is donated from F. Okay, so it's okay already. F atom donates the lone pair, okay, directly to H plus, yeah, or shared directly, so it's okay. Okay, 2 marks. Now, so let's move on. Okay, this a certain fluoroantimonic acid, yeah, contains 2 ions. Okay, and these 2 ions are given over there. Okay, draw the dot and cross diagram, yeah, for SpF6 ion. Okay, and then H2F plus ion. Include any lone pair that influence the shape. Name the shape of each ion. Yeah, so we are going to actually draw this. Okay, so SB. Okay, so if you are not sure, just always check. Okay, always check your periodic table. What is going to be SB? Yeah, SB. Where is SB? SB. Okay, SB. Okay, so this one is going to be from group 15, so 5 valence electron. Yeah, that is important already. Okay, once you know that, okay, 5 valence electron. Okay, I have 5 valence electron. Do have a look at this negative. Yeah, negative means there is 1 more electron coming in from outside. Okay, so it means you have 6 electron. So SB, okay, has 6 electron. Okay, and then we are going to join with 6, okay, F6 F ion. Okay, sorry, there are 6 F. Okay, there's 6 F. So what we do, dot and cross diagram. Okay, I just put like this. Yeah, okay, they want to draw dot and cross diagram. Yeah, so no need to follow the shape. Okay, so there are 6. So 1, 2, 3, 4, 5, 6. Yeah, just try to make it nicer a bit. Yeah, hold on. It's okay lah. Okay, so F. Okay, I will just write down F. All these are F. F. Okay, must have 1. Okay, then they have like this. 1. Yeah, basically you see. Yeah, I'll do first. 1, 1, 1. So now I'm going to use the dot. Yeah, of course for you to see only. Yeah, okay, but I'm just going to put 1 dot, 2 dot, 3 dot, 4 dot, 5 dot, okay, group 15, yeah. So another dot must be special, yeah. So I can just put, because it's coming out from some other places, yeah. So it's going to be special, I put it over there. And then, okay, because the electron is coming from somewhere else, this entire thing must be written as minus. Okay, so what is the name of the shape? Yeah, so this is what we call as, okay, 6 bonding pair. Yeah, 6 bonding pair. What is the shape? Jonathan, are you there?
Yes.
Yeah, what is the shape? Octa what? Yes. Okay. Your exam, okay, is going to be coming soon, yeah. So Vivian is asking, sir, we can have 11 electron on valence? Yes. Okay. Do remember last time I told you about expansion of octet, yeah. So the expansion of octet can happen. So you do not need to make sure that it must have only 8 electrons in total. No. Okay. Do remember, okay, the moment that you have, you see, yeah, I'll tell you a little bit about the expansion of octet. Okay, so 1s2, okay, that's 2. 2s2, 2p6, that's why they say 8. That's why we write down 2, 8. Then after that, 3s2, 3p6, then we have 3d10. That's supposed to be 18. Okay. So do remember the expansion of octet that we are talking about. Most of the time we are talking about this, okay, 8. But the principal quantum shell number 3 also have the subshell of D, yeah. So they can expand all the way to 18. Okay. So I hope that answers your question, Vivian. Yeah. So this one can go not only octet, okay, it can go all the way to 18. All right. Okay, octahedral, let's actually have a look at H2F plus, yeah. So H2F plus, F, okay. So I put F, and then there's 2H. So I'll just put 2H. Now, F, okay, is going to be group 17, 7 valence electron. Okay, 7 valence electron. Hydrogen, okay, they need, okay, they have 1, they need 1, yeah. So I just put, yeah, they have 1, so they need 1. So let's say from fluorine must have 1, must give 1, no problem, yeah. But have a look at fluorine. Fluorine, yeah, they have, okay, they have 7 valence electron, and there is plus. It means one of the electron is went away, yeah, it went away. So it means instead of having 7, they have only 6. So 2 of the blue dots over there, okay, is already there. So you need to actually write down another, you need to make 6, yeah. So you need to write another 4, okay. They will become like this, okay. So what is this shape? Okay, this is going to be 2 bonding pair, 2 lone pair, okay. So 2 bonding pair, 2 lone pair. Ashana, what is going to be the answer? 2 bonding pair, 2 lone pair. Or Wilson, this is similar to what example? 2 bonding pair, 2 lone pair.
1 also like.
Okay, similar to water, yeah. 2 bonding pair and 2 lone pair. Okay, similar to water. Okay, so if it is similar to water, the shape.
Is the shape non-linear then?
Yes, yes. So it's non-linear, yeah, non-linear. Okay, let's look at the answer. Yeah, based on the new syllabus, you only need to mention non-linear. If the answer key mention V shape and so on, it's not accepted anymore, yeah. So we will follow the new syllabus. Okay, so you see here, the answer is going to be, okay, octahedral, so correct. Okay, can you see band and V shape as the answer? Yeah, this was last year. That is the answer for last year. But, okay, for you, now you cannot mention band or V shape. Okay, it must be non-linear. Okay, please take note of this. Yeah, very important. Yeah, in the marking key, we will not include V shape, we will not include bend shape or whatever shape. Yeah, it's non-linear. Yeah, non-linear. Now, next question. Okay, before that, let's look at the bond angle. Yeah, bond angle for octahedral is 90 degrees. But how about the bond angle for this non-linear? Crystal? What will be the bond angle? Crystal, are you there? Yeah, Crystal, what is the bond angle for water? Do remember, okay, CH4 tetrahedral 109.5. Okay, ammonia 3 bonding pair, 1 lone pair, 107. Water, memorize, okay, it's going to be 104.5. Okay, so make sure you remember this. So if it is going to be linear in this case, okay, it's non-linear in this case, it will be 104.5, yeah. Okay, I'll continue. Yeah, I'll continue. Now, hydrogen fluoride has a much higher boiling point than hydrogen iodide. Okay, you see hydrogen fluoride, okay, have higher than hydrogen iodide. Both of them are polar. Okay, both of them are polar. Okay, what is the difference over here is this is containing hydrogen and F. Okay, so do remember hydrogen with N, O, and F. Okay, can form hydrogen bonding. Okay, so this one cannot form hydrogen bonding, so they have PD. Okay, but this one, okay, has hydrogen bonding. So you just need to mention, yeah, this one I need to be mentioning this to you, yeah. Now, previously in the previous class, I have mentioned this. Okay, let's say for example, in exam, okay, let's say in life, yeah. Okay, let's say you have a boy A and you have a boy B. And then this one girl likes boy A and then go and couple up with this boy A. The question is why the girl is attracted to boy A. Okay, why the girl is attracted to boy A. And then the answer is because boy B is ugly. Can we accept that? The answer is no. Okay, when they ask why, okay, boy A is selected, rather than comparing to boy B, you should say boy A is more attractive than boy B, or boy A is more handsome than boy B. You focus the answer towards boy A. You do not focus the answer towards boy B because they are not actually asking about boy B. So similar to that, okay, you see this question, hydrogen fluoride has higher boiling point than hydrogen iodide. It means the focus is hydrogen fluoride. So you don't go and explain too much about hydrogen iodide. You don't go and answer that, oh, hydrogen iodide is polar and contains PD. That's why. Yeah, no. I don't want you to answer like that. Okay, what your answer will be is going to be hydrogen fluoride is a polar molecule, okay, and can form hydrogen bonding, okay, with other HF molecule. Therefore, it requires more energy to be broken. Now you explain little bit. Once you actually explain the main thing, now you explain, okay, hydrogen iodide only, okay, has permanent dipole, permanent PD, permanent dipole, permanent dipole bonding, and no hydrogen bonding. Okay, that is our answer. Yeah, 2 marks. Okay, let's have a look at the marking key. HF, you see here, the main thing is about HF. HF exerts hydrogen bonding, which is stronger intermolecular forces compared to permanent dipole PDPD in HI. So higher energy is required to break the forces of attraction. Okay, are we allowed to only write it as PDPD in exam? Okay, you are not allowed. Yeah. Okay, so do remember. Okay, you are not allowed PDPD. Okay, you must write full. Okay, even now when I'm writing, I'm not writing PDPD also. Yeah. So even this one HF. Okay, if you can avoid, please avoid. Okay, during exam, okay, please avoid. Okay, hydrogen fluoride. Okay, you mention fully. Okay, but in this case, what is important over here is, okay, I think I explained this, but I didn't mention that hydrogen bonding is stronger than PDPD, but I did mention it requires more energy to be broken. So a better answer will be, okay, to compare, yeah, because hydrogen bonding is stronger than permanent dipole bonding, yeah. So maybe this answer is not so good also. Okay, so you can just say it's a polar molecule can form hydrogen bonding, which is stronger. Okay, you just add stronger than PDPD. Okay, then after that you continue. It's okay. It's a very good answer already. Okay, this will give you the 10 marks. Yeah, 10 marks. Let's look at question number 5. Okay, so for many compounds, okay, the enthalpy change of formation cannot be calculated directly. So they actually use the enthalpy change of combustion. Yeah, so it can be found from a calorimetry experiment. Okay, in which the heat energy is given off during combustion is used to heat a known mass of water, and temperature change is recorded. So basically what they are telling Q, okay, you can use this formula mc delta T. Do remember, okay, this mc delta T, the mass, yeah, the m is going to represent for the mass of water. Yeah, our assumption over here is all the energy that is used, okay, to heat, yeah, the mass of water, okay, is going to be coming from 100% from the reaction itself. Yeah, so that is our assumption. Yeah, so that's why we use the mass, okay, of the water and the temperature change of the water. Okay, so the first question, explain the meaning of the term standard enthalpy change of combustion. Enthalpy change, okay, so you need to explain that. Yeah, enthalpy change is going to be the energy, okay, the energy change, okay, or in this case combustion. Yeah, so combustion is going to be the energy that is released. Okay, so if you want to write release also can. Okay, the energy that is released, okay, by 1 mole of a compound, or you just say when 1 mole, okay, when 1 mole of a compound is burned completely by excess oxygen gas under standard condition, because we still need to talk about standard under standard conditions. The standard condition that we meant over here is at 25 degrees Celsius and 1 atmospheric pressure. Okay, so that is going to be the definition. So if you look at the marking key, okay, let's have a look at the marking key as well, so that we can double check, okay, how much is the mark that will be allocated. So here, okay, they say that the enthalpy is the energy change, okay, when 1 mole of a substance, okay, reacts with excess oxygen, okay, and under standard condition. So they didn't say energy that is released, yeah, but there is energy change. So if you, I think better, okay, if you do not know, just okay, you want to make it as general, yeah, as general as it is, so the energy change, okay, when 1 mole of a compound is burned completely, that will be a better answer. Yeah, so the 1 mark, okay, is given, okay, for 1 mole of the compound, and then burn with excess oxygen gas and under standard condition. Yeah, 2 marks. Now write the equation for the complete combustion of ethanol. So ethanol C2H5OH is completely burned with oxygen. So ethanol will give you carbon dioxide and water. Yeah. So when they are completely burned, do remember, okay, enthalpy of combustion 1 mole of ethanol, cannot be more than that. So this one will be 2, okay, 2 carbon, okay, hydrogen, that's 6, okay, on the left. So I put 3 over there. The last one that I balance is oxygen. Oxygen on the right is going to be 4 and then 3, 7 on the right. Okay, and then there is 1 here. So I need 6, so I just put 3 there. Okay, so this will be the equation. And then, okay, ethanol, okay, ethanol is going to be in liquid form. Okay, and then this is gas, okay, when burned it's going to be in form of steam, yeah, water in form of steam. Now in an experiment to determine the enthalpy change of combustion of ethanol, okay, so you have this, yeah, be careful here, yeah? You do not use 0.23 grams for the Q equals to MC delta T, yeah? That is actually something that a lot of students make mistake. Okay, so you are going to actually increase the temperature of 100 gram of water by this, yeah, this is delta T. You do not need to convert this into Kelvin, yeah, please remember. Okay, and temperature change, okay, whether in degrees Celsius or Kelvin, doesn't matter, it's still the same. Okay, it's just a change. Yeah. So in this case, okay, we are going to calculate the heat release Q, okay, during the combustion of this. So this one, don't use this mass, okay, because we are going to use Q equals to MC delta T. Okay, this is given just to confuse you. Okay, so 100 gram, okay, 100 gram, not even 120, not even 100.23, yeah, don't go and add them together, yeah, no. Okay, the C is going to be, you check, 4.18, okay, it's given in the question, okay, so you can double check over here. All these are given, okay, the specific heat capacity of water, okay, 4.18, okay, and then delta T, they have given 16.3, that one just changed to Kelvin, yeah, it's Kelvin actually, yeah, the degree Celsius or Kelvin doesn't matter, yeah, so it's just a change, and you find the value, okay, so the value you will get in joule, do remember that as well, okay, so this one, if I calculate quickly, okay, I just put it over here, okay, so 100, okay, times 4.18 times 16.3, okay, that's going to give me, okay, 6813.4, 6813.4 joule. Okay, so that is going to be my energy. So in this case, they say 4 to 5 significant figures. So I will just maintain this one, 6813.4. Okay, calculate the enthalpy change, okay, on burning 1 mole of ethanol. Include a sign in your answer. Yeah, previously you don't include the sign, it's okay, because they say heat release, yeah, is understood, it's negative. Okay, but okay, in this case, you need to include the sign, must be negative. Why? It's exothermic reaction. Heat is going to be, temperature is going up. So just put, okay, the sign over there. Don't actually forget. Okay, so now, okay, we know that for this amount, 0.23 gram, okay, you have 6813.4 joule. Yeah. So I need to find for 1 mole of ethanol. So first, okay, find out, okay, how many mole is this, yeah, so ethanol C2H5OH, okay, so 12 times 2, okay, the MR, 5 times 1, okay, plus 16 plus 1, so that's 24 plus 5 plus 17, okay, so that's going to be 29 plus 17, 46, okay, you get 46, okay. So that's going to be your MR, okay, 46, okay. So you divide by 46, okay, 0.23 divided by 46, okay, that's going to give you Okay, if you want to keep it as 1/200 also can. 1/200 mole, okay, gives you 6813.4 joule. Yeah. So I want for 1 mole. Yeah. So 1 mole, okay, is going to be, okay, you just times by 200. Okay, times by 200 times by 200 here. So 6813.4 times 200. Okay. 6813.4 times 200. Okay, you will get 1362680 joule. You need to change it to kilojoule. Okay, so joule. So it's going to be 1362.78 kilojoule. Okay. So in this case, you want to keep it as a give full also, okay, doesn't matter. Okay, or you want to give 3 significant figures also can, okay, but I'll prefer, okay, to leave it like this. Yeah. Now, suggest 2 reasons why the value of enthalpy change of combustion of ethanol determined by simple laboratory calorimetry experiment is likely lower, okay, than the true value. So they say that, okay, most of the time when you do this enthalpy change of combustion, yeah, using the simple laboratory experiment, is likely lower than the actual true value. So in this case, you just can actually say, okay, the reason might be, okay, there might be many reasons. Yeah. So one of the main reason is there is going to be heat loss. Okay, so there is heat loss to the environment. Okay, so not 100%, okay, the energy, the heat is given to the water, is transferred to water. There is a heat loss. And then there might be reason, like for example, we are not doing it at standard condition. Yeah, so it's not, maybe it's not at 25 degrees Celsius and it is not at 1 atmospheric pressure. Maybe there is device, okay, that we use, okay, cannot actually measure, okay, like for example a thermometer and so on. Okay, so there may be a lot of reason over there. Okay, let's actually look at, okay, the reason that they mentioned in the marking key. Yeah, so have a look at, okay, the answer here. Let's check also the answer. Okay, this is correct, and then this is going to be negative 1362.78. yeah, so this one they put 0.7.8 supposed to be, yeah, but anyway it's correct. Now 2 reasons, okay, heat loss, okay, you see, okay, heat loss to the surrounding, and then, okay, not all energy, okay, is lost as heat. Okay, so or they say that ethanol, okay, may be evaporated. Okay, some of the ethanol, because they are volatile, they evaporated, and then the ethanol is impure. Yeah, so these are the reasons. So one reason, okay, not, okay, all the heat, okay, not all the heat, okay, absorbed by the water, or you can answer there is heat loss to the surrounding. That's 1 mark. And another one is going to be, you can mention that ethanol, okay, is volatile. Okay, and therefore, okay, the number of moles is actually lower. Yeah, so ethanol is volatile. Okay, therefore, okay, some ethanol might have evaporated. Okay, so might have evaporated, so that is going to make this value, the number of moles, is smaller. Okay, so that will be different. Okay, and then ethanol is impure, not all the energy is lost as heat. Yeah, so all this, okay, you can actually put it as your answer. Yeah, next. Now, one of the important steps in contact process is the manufacture of sulfuric acid. Yeah, is given. Yeah, because for contact process we have total of four equations. Yeah, so first is sulfur plus oxygen to give you SO2. Second is this one, okay, plus O2 to give you 2SO3, and then SO3, okay, they will react with concentrated sulfuric acid to give you oleum. Okay, so this is oleum, and then this oleum, okay, they will react H2O7, okay, they will react with water to give you 2 moles of H2SO4. Okay, so this is going to be the reaction, yeah, for contact process. Okay, but only the second equation, yeah, will require the catalyst. Okay, which is the catalyst is going to be okay, the catalyst that is going to be used for this is vanadium pentaoxide. Yeah, so now, okay, you have 10 moles of sulfur dioxide. Okay, 4 moles of oxygen are allowed to react in container of 400 degrees Celsius. So after equilibrium has been established, the total pressure was 200. Yeah, and then the mixture of gases contained 3. Yeah, so later when we calculate, we will use this information. Okay, define equilibrium. Okay, so to define equilibrium, okay, it's going to be a system, okay, that is going to be dynamic. Okay, dynamic, the reaction of both forward and backward reaction is still continuously happening, and then, okay, the rate, okay, of forward reaction is the same as the rate of reverse reaction. Concentration of the reactant and concentration of product remains constant, and also, okay, it's going to be in a closed system. So all this, okay, we need to actually put it together. Okay, so if you look at the answer required, okay, let's look at the answer required. Okay, they just put only one. Yeah, so only one. So probably my answer will be, okay, a system. Okay, a system where, okay, the rate of forward reaction is the same as the rate of backward reaction in a closed system. Okay, what is closed system? There's nothing going in, there's nothing going out. So that is actually a closed system. Now give the expression for the equilibrium constant, yeah, Kp for this equilibrium, because this is actually gas. So we will use Kp, so we will use the partial pressure. So partial pressure of SO3 to the power of 2, okay, divided by partial pressure of SO2 to the power of 2, and then times partial pressure of O2, okay, to the power of 1. Okay, so calculate the number of moles, okay, present at equilibrium. Yeah, now we have to use all this information. Okay, so I'll just put it down over here. Okay, 2SO3. We will use the ICE method. Okay, initial, I for initial, C for change, E for equilibrium. So initially, okay, they put 10, okay, 10 over here, and then 4 moles of oxygen. So initially there was 0. And then after equilibrium, the total pressure is 200, and the mixture of gases contains 3 moles of sulfur. Yeah, so it means at equilibrium you are going to have 3 moles. So what is the change over here? The change is going to be plus 3, and you can see this is 2 mole. Okay, this is going to be 1 mole. This is 2 mole. If there is plus, okay, do remember, for product there will be plus, for reactant there will be minus. Okay, they are going to react. So 2 moles, 2 moles, so same ratio, so minus 3. Yeah, and what is the change over here? This is going to be half of it, so 2 to 1. Yeah, so the ratio is going to be minus, okay, because it's still reactant, so minus half of it, minus 1.5. Yeah, half of 3. Yeah, half of 3. So 4 minus 1.5, that's going to be 2.5. 10 minus 3, that's going to be 7. So all these are the one that we will use, okay, for our calculation. Okay, but do remember, okay, we will use partial pressure, yeah, but now they say calculate the number of SO2 and O2 at equilibrium. So number of moles of SO2 at equilibrium is going to be 10 minus 3. You can just put it over there, 7 moles. Number of moles of O2, okay, equals to 4 minus 1.5, which is going to be 2.5. Okay, so the working, okay, you can actually, okay, I wrote it over there, but actually we can put it over here. Okay, this is our working. Now, calculate the partial pressure of each gas present at equilibrium. Yeah, so if I want to calculate this partial pressure, so partial pressure of let's say SO3, okay, partial pressure of SO2, partial pressure of O2. Okay, so in order to calculate this, we have to use the total number of moles. You see, all these are, okay, number of moles. So 7 plus 2.5, total number of moles. Okay, total moles is going to be 7 plus 2.5 plus 3. That's 12.5. Okay, so everything will be divided by 12.5. Yeah, so this one, okay, I copy, I paste it over here. Okay, I paste it over here. Okay, so in this case, okay, sulfur trioxide, that's 3, so 3. SO2 is going to be 7 at equilibrium, and then PO2 is going to be 2.5, and then you need to times with the total pressure. The total pressure they have given 200 kilopascal, so 200 kilopascal. And then you just need to find out what is this, yeah. So now I'll calculate quickly for you. Okay, so 3 times 200, okay, and then divide by 12.5. Okay, the answer is going to be 48 kilopascal. And then 7 times 200, okay, and then divide by 12.5, you will get 112. And then 2.5 divide by 12.5, okay, and then times by 200, that's going to be 40, okay, kilopascal. So these are the partial pressures for each of the gas, and then they ask you to calculate the value of the equilibrium constant. So this is the, you just need to bring this, okay, this entire thing. So I'll just copy and then paste it over here. Okay, so this is our Kp. Okay, so I just need to put, okay, the partial pressure in. Okay, so this one is going to be 48 to the power of 2 divided by, okay, SO2 is 112 to the power of 2 times O2 is going to be 40. Yeah, so let's calculate. 48 to the power of 2 divided by 112 to the power of 2 times 40 bracket. Okay, so this one is 0.004592. Okay, and then this one, okay, Kpa to the power of 2, Kpa to the power of 3, you cancel. Okay, this one is Kpa, so it's going to be kilopascal -1. So let's actually change it into pascal only. Yeah, so 1 2 3 4.592 pascal -1. Okay, that's going to be, if you change it to 3 significant figures, so that's going to be 4.59 Pa -1. Okay, that's going to be the answer. So Kp and the unit, yeah, Kp is 4.59, the unit Pa -1. Okay, so let's actually check the answer. Okay, so 112, 40, 48, okay, and then 4.59 kPa negative 1, okay, or you can actually use, okay, Pascal, okay, negative 1, okay, 4.59 alone. That is all okay. Yeah. So now, okay, let's actually move on. Now, acid rain, okay, is caused by a chemical reaction, okay, that begins, okay, when the sulfur dioxide and nitrogen oxide are released in the air. Okay, for nitrogen dioxide, when it reacts with water, yeah, the products will be nitric and nitrous acid. Okay, it is a disproportionation reaction. What is a disproportionation reaction? So basically, disproportionation reaction is going to be a reaction, okay, where a substance is the same substance is being oxidized and at the same time, okay, being reduced. Okay, so disproportionation is going to be, okay, that's our okay, that's the idea. Yeah, let's see what is required in the marking key. Okay, so they say that a substrate itself undergoes both reduction and oxidation reaction. So you just say a substance that undergoes, okay, or a reaction where the substance, a reaction where substance undergoes both oxidation and reduction at the same time. Show in terms of oxidation number, the reaction above is disproportionation reaction. So you need to calculate, yeah, so oxidation number, okay, nitrogen over here. So X, okay, then plus 2 times negative 2, oxygen is negative 2 equals to 0, X minus 4 equals to 0, X equals to 4. So from 4 to 1 and from 4 to what? Okay, so this is for NO2 to, okay, let's say HNO3. This is for NO2 to HNO2. Since, okay, the first reaction is what, and the second reaction is what, therefore it is a disproportionation reaction. So let's calculate. Okay, so HNO3. Okay, HNO3. Okay, so this one. Okay, plus 1 plus X. Okay, 3 times negative 2 equals to 0. Okay, X minus 6 plus 1 equals to 0. X minus 5 equals to 0. X equals to 5. So this is 5. Okay, therefore the first reaction is plus 4 to 5. Okay, so it's going to be oxidation, the first one. Okay, the first one is oxidation. And the second reaction, okay, from 4 to what? Okay, so HNO2, 1 plus X plus 2 times negative 2 equals to 0. Okay, 1 plus X by minus 4. X, okay, minus 3 equals to 0. Okay, X equals to 3. So this one 4 to 3. Okay, therefore, okay, this one, the second reaction is going to be reduction. Okay, therefore it's disproportionation reaction. Okay, done, yeah. So end of the question. Okay, so just roughly we check the marking key again. Okay, you see 4 to 3. Okay, 4 to 5. So better, okay, I think one of the things that is really important over here is to put this one plus 4 plus 5 plus 4 plus 3. Yeah, so that's it. Yeah, we have went through the question paper. Okay, hopefully you can understand. Okay, so good luck for your exam. Yeah, see you, bye.